Okay, so now we're going to start working on nuclear chemistry, and nuclear chemistry is kind of its own thing. You may wonder why it is that you're trying to learn this, and it's actually quite simple. That is that with nuclear chemistry, you can see different things in the body, and different sections of your body may show different types of anomalies in the presence of different types of nuclear reactions. In addition to that, if somebody has been overexposed to nuclear radiation, that can cause problems. So it's good for you to know about. So let's start with the basics definition, and that is what is radiation? So radiation are small particles or very high energy that's caused by a breakdown of an unstable isotope. So if you remember, an isotope is something that has a lot of different neutrons. There are certain atoms that if you have a lot of extra neutrons, they can be relatively unstable and they just kind of spontaneously come apart. So a radioisotope, this is a specific isotope that breaks down and emits radiation, and what we call that is spontaneously. That does not mean that it just happens. It just means that, that it just happens instantly, sorry. It means that it happens with a certain amount of precision of moving forward. It doesn't have to do with the timing itself, okay? Usually we're talking about large atoms that are radioactive. So you may be familiar with uranium as being unstable, or certain types of platinum. Those can be, not platinum, palladium, excuse me, that are unstable, that they will sort of emit different types of radioisotopes. So, for example, another example that you may be less familiar with, there's two different isotopes of chlorine. So we have 35 and 37 that are relatively stable. However, the one in between, 36, it hardly exists for long because it's radioactive. So all of those are going to have the same number of protons. We're not talking about the different numbers of electrons. We're talking about different numbers of neutrons, okay? So that's what can make something a little bit just unstable, and that's just sort of what happens. The term radiation is quite broad, and it means a lot of things. There's a lot of things that are encompassed in that word. So let's go through some of those definitions. And before we get to this, I would say this is something that you probably need to know. Do you need to memorize it? That depends. If you do enough homework, you're probably going to know it well. So yeah, you do have to commit this to memory. So if we start with the alpha particle, this is, sorry, I can't highlight unless I scroll that down some. So we literally call that with an alpha. It kind of looks like a fish there. This is a type of particle that's very specific. Well, all of these are. They are known as helium. So helium-4 would both mean the same thing as the alpha particle, because that's what an alpha particle is. So you're actually emitting kind of a helium atom. So this is what's going to happen when a nucleus ejects 2 protons and 2 neutrons. Obviously, this is a very common thing, or we wouldn't have a term for it. So the mass is going to be 4. The charge is going to be +2. So I say a helium atom, but it's got no electrons. So helium would definitely have electrons, right? So that's obviously not as stable as like if you would have helium gas. So that's what an alpha particle is. That's the definition of it. If we move to a beta particle, this would be abbreviated as B. And the way that we would otherwise designate beta particle is this 0 at the top, -1 E. what that says is there's a very high energy electron that is there. The charge of -1 is designated by this guy right here, that -1 that's down there. It has no mass. It's just an electron. Well, it's got the mass of an electron, which is teeny, teeny, tiny. So what's happening here is that a neutron is splitting into a proton and an electron. So it holds on to that proton, but the atom loses a neutron and it's going to gain a proton. So that will actually change the chemical designation of it, because remember, your atoms are designated by how many protons you have. Okay, these must seem strange when you first think about it. Okay, the next is a positron. This is kind of rarely seen, but it happens. And we call this beta plus. And the reason why is that we would designate that as an O0 E with a +1 on the bottom, which means that that would be a positively charged electron. This is what we refer to as antimatter. You may have heard that term before, and these scary sci-fi movies. It's antimatter, it's an antimatter chamber, whatever. Well, it is exactly what it sounds like. It's the opposite of matter. So what that means is that if this hits a real electron, they literally cancel to make nothingness. And how could it not hit an actual electron? They're everywhere. It's going to emit a lot of energy when that happens. Thankfully, that's relatively rare. Thankfully, because that way we can actually, not worry about energy just erupting next to us without it being a little bit scary, right? That would be a little bit scary if it happened more often. So what's happening is that an unstable proton is going to split into a neutron and a positron, okay? So it may be like, why are you writing these in specific ways? You might be asking yourself that. Like these 4He, this guy right here with the beta particle, and then right here we have the positron. Well, this is going to make life a lot easier when we go to actually balance equations. Just making sure that you're aware of that. So this resulting neutron from a positron will stay in the atom. So the atom basically loses a proton and gains a neutron. So see, those two things are kind of similar to one another there. One's going to gain a proton, the other one's going to gain a neutron. I'm going to scroll up here. Okay, so gamma rays. These are a lot easier to actually deal with in reactions, at least, because gamma rays are just energy. So they look like this weird Y, and it's a 0 over 0. And what that is it's just pure high energy. It is on the electromagnetic spectrum. No particle changes are going to happen. Other things that can happen is that you can actually emit a proton by itself, which is 1 over 1 hydrogen, or just P. Or you could just have a neutron that comes out, which is 1 over 0 N, or just N. And so that pretty much gives you the wide array of things that we can have. We probably need to practice using them, though. Okay, so here's some basic stuff before we go into too many problems. So when radiation hits the body, it's going to affect the cells in rapid division the most. So things like reproductive organs, your bone marrow, which is where you make red blood cells, your skin and hair, digestive tissue. So if you've ever heard of somebody who is undergoing radiation, that's exactly the types of things that they can get sick with. Children can also be highly affected. Radiation affects cancer cells. Why? Because cancer cells are basically cells that are rapidly dividing uncontrollably. So by emitting radiation upon them, that in theory should help them not do that anymore, so it stops that. Something to be aware of that I think is kind of interesting is that radiation can cure cancer, but absolutely can cause cancer too. Why? Because since we have this high energy types of molecules, subparticles really, around, they can affect the way that cells behave and the way that they work. So it is very, very important. If you are in the medical field working with radiation, or even patients in contact with radiation, you need to use proper shielding. The best proper shielding you can get is distance. The further away you get from radiation, the better off you're going to be. If you're just getting radiated with alpha particles, that can be easily stopped. That's your just clothing is going to stop that. Like it doesn't allow, your clothing would not allow alpha particles to get through to your body. Beta particles, on the other hand, are higher in energy, therefore heavy clothing is going to be needed. Gamma particles, that's going to go pretty much straight through you because it needs concrete or lead to be stopped. So make sure, again, to protect yourself if you ever, come in contact with these things. And it's, as I said, these things are really used a lot when it comes to medicine. Okay, so let's try some different types of reactions and see how these kind of work, okay? So if we're looking at an alpha decay reaction or equation, let's say that we're starting with Pu and we've got 240 at the top, 94 down below. Well, let's say that we're getting an alpha decay off of that, which would be helium, which has a 4 up top, 2 down below, and then just your He. Well, here's the thing. This 240, sorry about moving that, this 240 must be equal to what we have at the top on the right-hand side of the equation. So 236 and 4 would be the same thing as 240. So if you add those together, that's going to be the same thing as 240. So let's say that you just know that there's going to be an alpha decay, but you don't know what else you're going to get. Well, basically you can take the 240, subtract out the 4 to give you the 236. So I'm just making sure you realize that, okay? And again, on the bottom, it's the same thing. So we have 94 down here. We know that we have 2 down here. So that means that this would have to be 92 because 92 plus 2 equals 94, okay? And remember, whenever you see in chemistry this little arrow here, that kind of means, hey, the two sides are equal, right? So beta decay equations. Remember, beta decay is the result of a neutron splitting into an electron and a proton. The proton is going to count, so the atomic number will increase by 1. So here's how you would see that again. Let's say we start with carbon-14, which is used in a lot of like dating for things that used to be alive. We have a certain amount of carbon-14 in us. So this number up top, the 14, if we know that we're going to have a beta decay, that's 0. This number does not change, right? However, when we're looking at the bottom number, carbon has 6 protons. Since with beta decay, we have a -1 down here, then that means that we have to change the bottom number on the right-hand side to a 7. What that means is that you just change the identity of that atom, right? Because it's defined by what your proton number is. Okay? Okay. Positron decay. So let's say that again, we have carbon 10. Positrons have 0 up top. This number's not going to change. Everything stays the same. But since what we're doing is that we're taking one proton, and that's going to change to a neutron plus an anti-electron. That just thought is crazy, but that's exactly what's happening here. With this number being a 6, and this number being a plus 1, that means that that number had to change to 5. And so then you'd have to look at the periodic table and go, oh, well, the atom that has an atomic number of 5 is boron, so it's no longer carbon. Okay? So those are the ones that are the hardest because gamma decays are kind of really easy. This one is showing you technetium, and see it says 99M, and what that means is metastable. That means it's kind of stable. There's no mass changes here. The only thing that's happening, this all stays the same because this is just 0, and you have to just put out there that we've got 0, 0, and a gamma ray that's coming out of that, okay? So unstable elements can come from different sources. Some of these are going to be occurring naturally, like your carbon-14. Other things we specifically make. I know that there's several areas in hospitals where they can even make the technetium in the morning, or better yet, have that on hand in the morning. That would be a better way to say that. Man-made radioactive elements are made by forcing, which is basically you're bombarding a particular type of compound with other types of particles. Well, bombarding means that instead of having a product, we're putting that as a reactant. So for example, let's say that we had aluminum with 27 and 13. If we bombard that with a neutron, it would be part of the reactant side. And so we would add the top numbers together, yielding a 28 in this case, and the bottom numbers won't change. That's still 13. So instead of having the radiation occur on the product side, it's just occurring on the reactant side here. You could do the same thing with a proton, or really anything for that matter. So as I said, like just noting here, remember that the top numbers on one side of the equation must equal the top on the other side. Same thing for the bottom numbers, right? So other things that you probably need to be aware of is that when you're measuring radiation, that's usually done in a curie, or you may not have heard of this term before, and that's called a becquerel, which is BQ. That's what we usually use to measure radiation. In medicine, they also use the term rad, which is the radiation absorbed dose. Or sometimes they'll talk about REM, which is radiation equivalent in humans. So radiation sickness is a result of too much exposure. It is very serious. There's not really a way to reverse that. That's just sort of what happens. And so you need to be very careful with radiation. And that's why I stress to you, if you end up working in healthcare, please, please make sure you protect yourself. Okay, we'll talk about half-lives in the next video. And let me know if you have any questions. Thanks.